some times, then we will do other thing. Not photochemistry, Paterno Buchi. Okay. Paterno Buchi, this reaction is basically photochemical cycloaddition reaction. Let's us let's give one example. We have this carbonyl. This carbonyl upon reaction with this alkene under photochemical conditions. If we irradiate by H nu, then we are going to get these compounds. That is, it's a photochemical cycloaddition reaction. Photochemical just hold your patience. You will enjoy this chapter. Very good, very nice chapter topic. Photochemical cycloaddition reaction. We see it's a cycloaddition of this carbonyl with these alkenes, and it's initiated by light. So the reaction takes place with alkene. The alkene may be electron rich, electron deficient. Electron rich, or maybe electron deficient. Then reaction happened with the what? With the excited carbonyl. Excited carbonyl. And this excitation takes place because of non-bonding to pi star transitions. So we have excited carbonyl. That excited carbonyl add with the ground state of alkene. Alkene. So it's not that the alkene is going to be excited. It's a reaction between excited carbonyl with the ground state of alkene. And the reaction is non-concerted manner. It's don't happen at a time. It's not concerted. That's why. So we should keep 3 points in mind. Number one, that it's a photochemical cycloadditions. It may happen with electron-rich alkene or electron-deficient alkenes. That's the vital point. Is the excited carbonyl. That excitation happen from non-bonding to pi star transitions. That excited carbonyl combine with the ground state of the alkenes and makes the product. We'll look at details of this mechanism. Okay, so this is the carbonyl under our study, C6H5. We have irradiated this carbonyl with H nu. Then what will happen? This is very vital. This is going to first singlet state, and upon intersystem crossing, this is going to the triplet state. How is this triplet state? This is the triplet state. Let's say I draw the structure here, C6H5CO. Here is one unpaired electron, and here is another unpaired electron, the same state. That's why it's a triplet state. So this is what? This is excited triplet state. Excited triplet state. And this is going to bind with the alkene. We're going to add with the alkene. So we add this alkene now. C double bond CH2, CH3. What happens? Then it adds, it may adds in two fashion. I will tell later what is major, what is minor. But let's see the two fashion first. C O CH2 CH3. This is the alkene, and we have two phenyl group over here, C6H5, C6H5. We have, look, the spin state is on the same spin state, like triplet. And here also, that here this carbon ends add to the oxygen end. Here this carbon end will add to the oxygen end. Will come later, which is major and which is minor. The same thing. This is CO. Here it will be C, two methyl group, and this is CH2, C6H5. This is the same spin state. After that, spin inversion will take place. Otherwise, they cannot make a bond. Spin inversion. Then what is happening? We will have this CH2. Here two methyl group, and here it will have C6H5, H5 plus CH3, H, H, C6H5, C6H5. Okay, so this is happening after spin inversion. Just I have shown the overall picture. And here it is the major product 90%, and this is the minor. Okay, now the what are the steps that are associated with these kind of things that we should remember during this mechanistic study? Look, first one, it is molecule is excited to the singlet state, then it is going to the triplet state. After that, reaction happens on triplet state. Then what happens triplet state? That we can say there addition of two component or binding or attachment. Attach is in the best better term. Attachment of two component. After that, this is the important spin inversion, inversion, and then product. Okay, so this is the step that's associated with this mechanism. Now we'll come to a point. Look at the product. This is major, this is minor. What it happens to? The result is here. When this excited triplet state attached with this alkene in this fashion, that more substituted carbon attached with oxygen. See, the radical left 1, 2, 3, 4, 1, 2, 3, 4 y radicals is left. It's quite unstable. Why unstable? The radical here is a 1 degree radical. And look here, if CH2 attached with this oxygen, the leaving end of this radical is now 3 degree. And this is 1 degree. So we know that the radical stability, 3 degree radical is more stable than 1 degree. Then 1 degree radical. That's why This is the proportion at which on their yield. Okay, so along with these 4 points, that molecule excitations, singlet to triplet, then attachment, then spin inversion. Before that, it undergoes spin inversion. That's why it is not concerted. If this was concerted, there should be no time for spin inversion. And the stability of the product, is which part will be major and which part will be minor, that is governed by the step. This radical, living radical is 1 degree, that is unstable. This is 3 degree, that is quite more stable. That's why it produces this as major product. We should keep all these things in mind. So when go for mechanics study, slowly we'll go into some tricks using which we can approach the question very fast. First, we'll much emphasize on learning. I repeatedly say during my classes, if you don't know whatever the number of example you practice, you'll not be able to do it in the exam. So, and another point I had that this is not concerted. And another vital point that I showed, it transformation from singlet to triplet, it's happened for electron rich alkene, not for electron deficient alkene, electron rich alkene. So if you have a look on the alkene, it's electron rich alkene, electron rich, E rich. That's why this mechanism is applicable. If it is electron deficient alkene, we'll see some different mechanistic pathway. Here another example I'm showing. Let's us think is a furan. Look, here is one double bond also. The double bond also can act as on diene, sorry, not diene, at in on alkene. So this can behave as alkene. It's a alkene moiety. And look, it's a 5 6 pi electrons, means taking the lone pair over 5 atom. That's why it's a electron rich alkene. We can designate that as equivalent to electron rich alkene. If it electron rich alkene, for this molecule also it will go to the same pathway. So we have this carbonyl, photoradiation, singlet, then triplet. And after this, we have treated these molecules or excited stimulate state by furan. Then what will be the product? Is very simple. Just these things. Sorry, it will be 4 member. By mistake, it has been a 5 member. It is 4 member. Again 5 member. And we have two pages here. That is, furan also can be used for this kind of cycloaddition reactions. Now we'll take example of, not example, the detailed study also for electron deficient alkene. Electron deficient alkene. Paterno Buchi reactions for electron deficient alkene. Let us consider we have taken this carbonyl, acetone, and we have taken this cyano compounds. So this is electron deficient. Electron deficient. and the product that we are going to get is these things. Yeah, retention of stereochemistry. Both the sign will be in the same directions. And here the reaction takes place. First, the acetone goes to singlet state, and the reaction takes place here. So, how does it go to singlet state? Because of non-bonding to pi star transitions. So, for electron deficient alkene, the excited singlet state of carbonyl attached with the alkene. So, this is the excited singlet state. Excited singlet state. So carbonyl reacts with alkene with this S1 state. Now have a look on the mechanistic study. So we have a carbonyl here. Uh, okay. So upon light irradiation, it is going to excite, going to be excited. Then we have this nearby alkene. Then what is happening after that? This will be formed C minus an electron transfer from alkene to here. This is dot. Now as one electron transfer, this will be plus and this is minus. We are going to do this mechanism in details, but all the things are possible at this moment. So this is called exciplex. Exciplex. So first, for electron deficient alkene, an exciplex is formed. That is a charge transfer interaction. Okay, so this is charge transfer interactions. We are studying in so much details. If the question comes that this cycloaction proceed through which formation, if you know the information, that we know this is the exciplex formations. So how it looks like? Now let us think. Let us do it by electronic transitions. As the reaction is going to happen in a singlet state, so this is the pin state of a carbonyl. It is singlet, and here we have this alkene. So this is the HOMO of the alkene. From here, one electron is going to transfer from here to here. Thus the exciplex form. Here we have two electrons, and here we have one electrons. So this is the way the exciplex form. Exciplex formations. So again I am repeating. So for electron deficient alkene, the reaction is going through the singlet state, and it is the singlet state of excited carbonyl that is going to attach with the alkene. And during the state, one electron transfer from alkene to here. That's the exciplex formation. Reaction proceeds through exciplex. So let us take a real examples for that. So this is the carbonyl. Let us it is going to attach with this cyano, and upon photoirradiations, so this is going to be formed C double bond O and double bond CN, and we will have this kind of interactions. After that, we are going to get CN. Okay, now students, you may have confusion from which end it is going to attach. Just wait for a moment. After this, you will yourself will very easily understand that which end it is going to be attacked. Now, so this four-member ring, that is the in both cases we have seen a four-member ring formation. That is called, this four-member ring is called oxytens. This is called oxytens ring. Oxytens ring. So let us take up some examples for others kind of things. We have this carbonyl. Just it's a practice examples. We have this drying. Remember in case furan also was a candidate for these photochemical cycle additions. Just H nu, and through this it will be attached. This is the product we're going to get, and here we have one double bond. Similarly, if we have this is for cisdiene, and transdiene also works here. If we have a transdiene, then we are going to have this product. This one plus this one. After some time, you will realize that why this kind of way they are going to attach. Why this kind of orientation is favorable for the cyclization reactions. Now I am going to show you the mechanism for the next reaction. This is the carbonyl. We have irradiated that with the light. After that, we have two radicals. Now we have this alkene, CH2 double bond CH. So this is the way, one way, probable they can attach. And this is a singlet state. As a result, what we will have? We have these things. Oxygen, CH2. This is CH dot, and here CH double bond CH2. Here we don't need any spin inversions, but it happen on singlet state. CH2 CH, and in this fashion. Another thing may happen, just I am showing this part. After the formation of this radical, it's may attack here. Then if it's attack here, then we are going to have this radical. CH, now we will have bond formations. That's why we get these two products. And here, sometimes, most of the times, we see that the alkene is going to be attached photochemically with the carbonyl. I am going to show an example where alkyne also may be the partner. So this is quite new, that alkyne also can be photochemically added to the carbonyl. Photochemically added photochemically added to the carbonyl. How it can happens? Let us see with these examples. C6H5 C double bond O. We have benzaldehyde and we have used this alkyne. Here this is the thing that normally the book do not cover, but yet I am going to show. If I irradiate by molecules, then what is going to happen? We have photochemical additions. How it looks like that will be a dot. If you just practice in your home, just you can easily reach the mechanism. I am here just showing the structure. CHO C double bond C is a very simple mechanism. CH3 CH3. After that, just it's a this kind of reactions. As a result, we are going to get the 6H5, the double bond C is CH3, CH3. This is very simple. You also you can have a practice with these examples. C6H5. So normally what happens if the partner is not on alkene, then sometimes we get confused. Then what is this reaction? But now it will not be a problem for us. Then similarly H new, then we will have these ring formations. CH3. This is CH3, not OCH3. And same thing will happen. So just to write down a product yourself. That what we learned that except alkene, alkyne also may be a partner for these things. Now again I am going to show one more interesting examples in advanced manner. That's the intramolecular Paterno-Buchi reaction. Whatever we found is a intermolecular. That's one we have one carbonyl partner, we have one alkene partner that may be electron deficient, may be electron rich. They are in some same manner. It's quite slight change in their mechanism, but this happens. Here we'll see intramolecular Paterno-Buchi reactions. Intramolecular Paterno-Buchi reaction. How is that? Just have a look on this example. CH2 double bond CH. Okay, so look, one alpha, beta, gamma, delta, and this is on in and on. So the name is gamma delta enone. So it is given by gamma delta enone. So intramolecular Paterno-Buchi reaction is given by gamma delta enone. We should remember in mind. So what we need? Basically, we need one carbonyl compounds. We need one alkene. But these two partner is present in the same moiety. This carbonyl and this they present in the same moiety. Hence, in the presence of light or after irradiation of light, they'll undergo photochemical reactions. Then what will happen if we treat it by H nu? We are going to get these things. To dot, we will get double bond CH, CH2, O dot, C dot, CH3. Then what will happen? So if we just redraw the molecules, then you will see how the structure look like. The structure look like, wait, here I am going to redraw it. I remove it, this partner. Now I'm going to draw as this is CH2, CH double bond, CH2. And here I am going to redraw as, just because of space, I am doing the same work on the same molecule, on the same places, but you do it separately. This is O dot and this is CH3. Now, if O dot attach with these things, then what we'll have? We will have these things CH2, C dot, O dot, O, this. Now, this is quite stable. If O dot binds here, it will be primary radical. Now it is 2 degree, quite stable. After the what will happen? CH2, C, CH3. And what is the advantage of this photochemical reaction? There are something that we make some kinds of molecules by using photochemistry that is almost impossible by other technique. That's why this chemistry is very important. If you want to have a synthesis, this kind of molecules, this is very much challenging and painful. But just by photoirradiation and choosing our starting material, so you can easily get that molecules. So this is an example of intramolecular Paterno reaction. Now we'll see different kind of extra intramolecular Paterno reactions. This is one type of examples. Look, this is also another kind of molecules, and we have this carbonyl here, R. So this is such an entity that has one carbonyl and one diene, not diene, one in. So it's also good substrate for intramolecular Paterno-Buchi reactions. Then what is going to be? You know that first this is going to be O dot, C dot, R, and we have this alkene. After that, what will happen? This O dot is going to attach with these things. Then we will have these things. This is dot, this is C, this is O, it is going to bind here. We have R dot, not R dot, R and C dot. Now these two are going to bind. After this step, C, O, and these are going to bind and make a bond. So this is the product we are getting from intramolecular pattern of which intramolecular. Here I am showing you different examples. If we have these molecules, then what is going to happen? So this is a 7 member ring, double bond here. I am trying to show all the possible kind of examples from pattern Buchi. So you practice with one types of molecules and different types of molecules given. So it will be quite difficult at that moment. And another thing, okay, I will tell that later. Let's complete this work first. Then what we are going to have, we have this dot and this dot. And we have these things. Then what will happen? This is going to add here. You can ask why it is not going to add here. After the product formation, if you have a look on the ring, then you will get the answer. This is the common point that may arise if it attacks here. This will be just merely a 2-degree radicals. It will be better stable. But after that, okay, it is better stable, quite more stable. But after that, the ring that form that will be highly strained. Then what we going to have after this? We are going to have after this these things. This is O dot, C dot, not O dot. It is going to make a bond. That will be, it will no longer O dot. These things. This is no longer is dot now, but we have this dot. Now these two dot will now make a new bond. How that look like? So what we will have? We will have one 5 member ring. Let's do that. We have this 5 member ring. After the what we will have? Then we have one, two, three, four, five. Another 5 member ring. This looks like that. Look, one. This is one, two. This is two, three, three, four, five, four, five. So we have this product. So these two are very, very important for our competitive exam purposes. Why this is important? So it's a era of different types of name questions. That's why we are dividing over the normal patternology to paradigm to intramolecular patternology. And why this reaction is important? We know a very interesting aromatic compounds, a new type of molecule that is azulene. Just paradigm AL2 upon treating, it is going to be aromatic one. So this is not that we don't want to discuss, but yet as it's a time, just I showed you why this photochemistry. So we can easily make azulene from this kind of intramolecular pattern Noguchi, but it is very much difficult in other way. Azulene. So here we study three kind of pattern Noguchi, and one thing just for now I want to share the end of these examples. But after this discussion, we should remember in mind that it is not that excited alkene. So excited carbonyl plus ground state alkene. Every time, just have a look on the example. First, the carbon is going to be excited. Nothing changes alkene. That excited carbon is going to add with these alkenes. Look here. The carbon is excited. C dot O dot. That O dot is going to attach with the alkene. So that's the excited carbon, not excited alkene. So if three pairs is given, we'll choose this pair, not excited alkene. Alkene always in the ground state. So carbonyl will be excited. That we should remember after the discussions. And practice some more pattern of examples. Again, I am going to show another kind of pattern of examples. That is thiocarbonyl compounds containing. How to say that? We know that sulfur analog of oxygen is also possible. That instead of carbonyl, we are using thiocarbonyl compound. Thiocarbonyl compound. Then what is going to happen? Just irradiate with H nu. It's a non-bonded to pi star. Now this is a routine practice. Is going to singlet, then intersystem crossing is going to triplet. Then triplet state means what? C S. The spin will be in the same orientations. C6H5, C6H5. After that, we're using this alkene. Look, it's an electron-rich alkene. It is pH. If the alkene is electron deficient, then what happens? It retards the process of transforming S1 to T1. That's why intersystem crossing doesn't happen. The molecule will stop at excited singlet. That's why. Only we will reach the triplet state only when we have the electron rich alkene. Electron deficient alkene do not process or do not help the carbonyl or thiocarbonyl to get into the triplet state. Then this alkene will be added with that in the same fashion. Let's do that. It is pH. Which is sulfur, and then we have CH2. Now you understand why this will attach to this end. Now for this end, this radical can stabilize over this ring. That's why it attach with this carbon, and this leaving end become free at the carbon terminus containing 2-phenyl group. Now we need spin inversion. If spin inversion happen, then after the spin inversion, we are going to have a bond. C S C CH2 H5. So the spin inversion is a process that is associated with the electron-rich alkene, because it is the electron-rich alkene which helps the carbonyl to come into the triplet state. Once it's come into the triplet state, then it will have same spin. So spin inversion process will include or will involve if the partner alkene is electron rich. So what we did up to now, first we have started with the normal Paterno reaction. We have seen the different electronic transition. Then we have practiced some examples. Then we have discussed the Paterno reaction with different kind of diene. It may be cis or trans. Then we shift to the that alkyne can also be a partner for Paterno reaction. Then what we did intramolecular Paterno reactions. After that, we are seeing that it's not only the carbonyl, it's a thiocarbonyl that also take part or that also undergo photochemical cycloreduction reaction in the same manner. So it is the carbonyl and thiocarbonyl that take part in Paterno reactions. If the option is given, one is carbonyl given, one is third carbonyl given, another option is given both, so it should be both. So the CO and S is going to a main active partner. Why I call it a main active partner? Because it is the molecule that is going to be excited by light and becoming ready for the reaction. Then we'll see another fantastic example for Paterno reactions. This is very vast chapter, but if we can cover up all the things topics wise, then at least two or three questions you will have common from this. So in organic, if we have 4 5 questions attainable, it means almost it's quite better conditions. And the people that do not target, that this is the chapter we can easily have a look. It can be targeted. That's what I have just discussed. Means it's spectroscopy, it's geochemistry, it's photochemistry. Then I will take about heterocyclic. This is the part people normally do not target, but it can be easily done. That's why we should study it in details and practice some examples. Since aldehydes, what will happen? Here, CH, it is going to excite it. After that, what will happen? A dot and dot. And we have given a partner as furan. Initially, what you know, furan can be a partner. Now I am showing what will happen if furan be a partner. See, the attachment side is very interesting. And these examples I have taken from Terry and Sandberg. Some example I have taken from directly journals. Not some, lots of example I have taken directly from journals, and some I have taken from the books. In couple of classes, I will show that many examples from journal because this is a chapter that is targeted by the journal examples. Look, so this is the way. This is O dot means O center has attached with these sides, and it is look this fashions. O dot. Here we have CH dot AR dot. So it's a stable 1,4 biradical or diradical. Stable 1,4 diradical. Why it is stable? This direction, that radical can travel the aromatic ring. From this direction, the radical can travel into this delocalized system. That's why it's a stable 1,4 diradical. After that, the bond closure will happen. Here. And if we have a look on another possibilities, so this is the product. Another possibility means that this dot will attach here, not this dot. Let's see, carbon is going to attach here. Then what will happen? If carbon is attached here, then we are going to have this intermediate, that's CH, and this is going to be O dot and AR dot. So this is a stabilized radical, but this is not. So it is unstabilized. Here this end is stabilized. So that is not going to be. But here we found both the end is unstabilized. Okay. Another thing can happen if O dot attach here. I am showing it. So this is the neuron partner. I am telling that if O dot attach here, then what will happen? If O dot attach here, then we will have this dot as a result. O, this is C dot, this is AR, and this is dot. Then we are going to have these things. Look, here this end is stabilized but not this end. That's why this is also we are not getting, because they are stabilized. This can delocalize over this aromatic ring, but this dot don't have any delocalization option. So this is a unstable radical. Unstable radical. That's why we will have this only option stable one for diradical, and we have this product. This is very much important. Almost I have discussed all the means different kind of versatility of pattern of reaction that can have. Here I am going to show another example. ARCHO, H new, star. It is going to from excited state, and there we have this alkene partner. Okay, then what will happen? You look here, O, this dot here. As this ring, the radical in this ring do not have no more delocalized option. So we are going to get these things. CH, AR. So it's why not the reverse one? Means if we have this, sorry, just okay, as I have drawn, just let us extend it by one more line. Dot. I'm telling that why not these things? If this thing happens, then we are going to get O, a dot, and this is dot. As a result, we'll have these things. CH here. But we are not going to get this. Here what will happen? Look, two electronegative atoms in closer proximity. That's why these are not going to happen. Two electronegative atoms are in closer proximity. Are in closer proximity. So it is very unfavorable conditions. That's why it's not going to happen. So we'll have these products. Just have a look when the example is given or the assignment will be given, the question will be given. Just have a look on the substituent. If the radical, like previous examples, can be delocalized in both directions, then just try to find out the most stable one for the radical and just then make the corresponding bond. It will be the answer. Now we study a different kind of photochemical rearrangement. Today, maybe I will not be possible to cover up the whole. Today, I will cover partially. Next day, I will cover rest of the things along with some part from the